Good evening, everyone, and welcome to the next webinar of the Productivity and Profitability webinar series. This series is being brought to you by Meat and Livestock Australia and Agrista. This series is designed to assist sheep, cattle and goat producers to increase the productivity and profitability of their businesses. In this series, we'll provide you with timely technical information that's relevant to producers across Australia. My name is Tanisha Shields and I will be your host for this webinar. I am a consultant with Agrista based in Southern New South Wales. Tonight, we will be hearing from Dr. Jason Condon about how to make liming decisions on your property for maximum returns. Before I can hand over to Jason tonight, I'd like to cover off on a couple of the housekeeping items for tonight's webinar. Tonight's webinar is being recorded and a copy of the recording will be available on the Agrista and MLA websites. We invite you to ask questions of Jason throughout tonight's webinar. We'll address these questions at the end of the webinar. To ask a question, just head to slido.com and enter the code APR2024. Tonight's speaker is Dr. Jason Condon. Jason is an Associate Professor in Soil Science at Charles Sturt University and has taught and researched soils there since 1996. His research portfolio includes projects on fertiliser management, carbon sequestration, nitrogen cycling, salinity management in Vietnam, and the formation and management of soil acidity in Australian crop and pasture systems, in collaboration with New South Wales DPI, Holbrook Landcare, FarmLink and Central West Farming Systems. Thank you very much for coming on tonight, Jason. I'll hand over to you to get into the nitty and gritty of liming tonight.
All right, thanks very much. And welcome everybody. Thanks for having me. So I've done a fair bit of work with liming and acid soil work. Did my PhD in acidification in pasture systems more than 20 years ago, and then in the last sort of 5 years have gotten into more liming and management of it. So just starting off, just want to thank people that I work with at DPI. Name that's missing there is Helen Burns, who is retired at the moment, but DPI, the farming system groups in my local area, FarmLink, Central West Farming Systems and Holbrook Landcare. And then because acidity is a long-term issue, solution is a long-term solution, but funding cycles for research are really short. They're normally like 3 years, and a long-term would be classed as 5 years. And so we've had to sort of pull bits and pieces of money together to do the research that we've been doing. So we're grateful to get money out of GRDC and of course MLA to support some of the research that I'll show you tonight. And the National Landcare Program is the other major one. So I want to talk about a little bit about the problem that's acidity, what we can do about it, and prioritise, or how you might go about prioritising on your own properties. You know, what paddocks you might look at ameliorating. So what's the problem? When we talk about acidity, largely it affects plant growth, and it does that through affecting nutrient availability. So on our little graph here, we've got pH 4 on the left, going up to 9 on the right, and 7 in the middle. So 7's neutral, less than 7 is acid, more than 7 is alkaline. And on the y-axis going up, we've got plant availability. So as things go higher up the y-axis here, they're becoming more available to the plant. And so pH affects nutrient availability a lot. And as a rule of thumb, it affects metals. Metals become more available at low pH. And I like to remember that as, you know, if you stuck a steel rod in a bucket of acid, that solid steel rod would eventually dissolve into a liquid, and liquids are, you know, kind of able to be taken up by plants. So metals become more available at low pH. So here we have iron, copper, zinc, manganese, and aluminium. So some of those things plants need, and some of them they don't. For example, aluminium, plants don't need it. But of course, if you get more of them and they become more available, you can create toxicities. And in terms of acidity, the two that hurt us most that we know about are aluminium and manganese. Going the other way, and really the only thing that goes the other way that we need to know about, is molybdenum. And so it is unavailable at low pH, but becomes more available as you get closer to 7. And then there's phosphorus, and it behaves like a bell curve. And so it's more available, plant available in more neutral pHs, and it becomes unavailable at low pH, often because it gets bound up with aluminium, and it's unavailable at high pH. And so you get these pH-induced deficiencies of molybdenum and phosphorus. Now, why I'm telling you about that, because they're deficiencies, they will respond to fertilizer. And the tendency for managers is to put Moly or P fertilizer on because they are deficient to overcome the problem, which fundamentally is acidity. And so if that is how you are managing acidity, you are only ever treating a symptom by putting on Moly and P. You're not actually fixing the underlying problem. And so eventually, if you're still productive, your system will acidify to a point where you'll get quite substantial failures, largely in legumes, and your microbes won't love you much either as you make your soil more and more acid through time. So this addressing deficiencies with fertilizer is very much a short-term gain, and it has long-term consequences, is what I want you to understand from that. And the other thing is that because of these deficiencies or that are induced by low pH, if you are operating at this low pH environment and you are putting on fertilizers that become unavailable at low pH, the efficiency of those fertilizer applications aren't very good. So you'll put them on, you'll get a response, but the response isn't as big as if you'd increase the pH to get away from the acidity problem. So your bang for buck is worse if you keep that acid soil. So what does that interaction do to plants? So this picture, as you can see, is lucerne. It's in the same paddock. It came from the same paddock. And on the left here, you can see it's much healthier than the stuff on the right. And we've got dig sticks here that have a pH indicator on them. The yellow is telling it it's about pH 4, and that's pH 4 pretty much all the way through, a little bit of green on the top. And in the better patch, you've got some blues, which are up around 7.5 in water, and then going into 6. So that's probably 5.5, 5.8 or something like that in calcium chloride. And then it's the lighter green tending to yellow down here, so it's still acid at depth. So what can we see? We can see that in an acid soil, the roots get pruned because there's so much aluminium, it stunts the root growth. And over here, where you don't have that, the roots grow nice and fibrous and dense and long. And on here, you can see there's little specks. They're nodules. So that's the rhizobia infecting the plant, fixing nitrogen out of the atmosphere for free. On the right, the acid affected lucerne, the plant's there, but there's no nodules. And so what does this do? You've fundamentally got a decrease in roots. And of course, if you've got a decrease in roots, you've got a decrease in water uptake and nutrient uptake. And so I like to talk about, once you get limited in root depth, you're effectively you're talking about the pot, the depth of the pot that you're growing this in. And so on our right, those roots went about 5 centimeters. So you're growing in a 5 centimeter pot. And if you're growing a plant in a 5 centimeter pot, you better get rain fairly regularly to keep that thing alive. Otherwise, it's going to suffer pretty quickly. Whereas if you've got a deeper pot, you've got a greater reserve of nutrients and water accessible by that plant. It's going to survive harsh conditions for a lot longer. So these things all combine to give you poor plant performance. Now, and so that's response to grazing. That's gain in dry matter through time, through the season, and gain in dry matter in response to the rain that you get. If a lot of legumes are quite susceptible to low pH conditions as well, and so they'll die out. And like this lucerne would have, dry conditions, even though it's a perennial plant, it will still die out. And so in the patches where the acidity still existed, there wasn't a lot of lucerne there. So you lose legumes. Then you have less nitrogen fixation coming into your paddock. You've got less organic matter because you've got less biomass. You've got less roots, so that's organic carbon in the soil. Less nutrients cycling, less nitrogen fixation. So you end up getting a biologically poor soil and nutritionally poor as well. These are all very, very bad things. And just a reminder that biomass, the more these things grow, as long as they can fix nitrogen, those nodules are there, the more biomass you have, the more nitrogen you fix. And so this is a significant problem if you're relying on these legumes to fix your nitrogen for you. And of course, I want you to ask yourself, well, what if I saw my pastures, performing badly, if they're not responding like they were? Maybe it's I've got this paddock that's not doing as well as the others, or I expected more from that. It used to be better and now it's not. So what's your response to that? I know some people where it's like, oh, it wasn't performing, so I gave it some more fertilizer and to see if I could get it to pick up, and it didn't. Or maybe it's a case of, it hasn't been doing so well. I'm not really sure why, but I'm going to wind back my expectations of that. I'm just not going to drive it so hard. And it's that's almost like, running the white flag up and surrendering. And so I put it to you that once you start seeing poor performance, it's an indicator that you need to go looking harder and looking at the soil. And importantly, like I've done in this photo, look at what the plant is doing in response to the soil that it's living in, because ultimately the plant tells you where the problems are. You just need to then work out what it is and what can I do about that problem. So equip yourself with like a garden fork that you can dig into the soil and tickle the plant roots out of the soil so you can see what they're up to, what they're doing, where do they stop, how are they growing, are they going sideways, these sorts of things. So how do we get there? How do we get to this problem where we've got acid soils? So some soils are naturally acid, and by that, their parent material, the stuff that they're made of, wasn't alkali to begin with, so naturally acidic. And so I guess some people are a bit luckier than others maybe. But fundamentally, and this is a really important point, agriculture is an acidifying business. It really doesn't matter what you do. I'm going to say if you're relying on agricultural production, selling stuff out of the paddock, you will be acidifying your soil. And you might be responding to that by balancing the acidity by adding lime. But if you're not, then you will be acidifying the soil. How fast it acidifies depends on the starting point, what the pH is or was when you took over that block of land, or when it got cleared and it started to be farmed. So the starting point, the buffering capacity of the soil's ability to resist change in pH. So that's different for various soils. And so the same amount of acid will decrease pH by different amounts depending on how well that soil is buffered. The more organic matter you have, and the higher the cation exchange capacity, which is a measure of basically clay and the reactivity of the clay in soil, the more buffered the soil will be. You can't control the clay. It's there. It's what was given to you in that soil, but you can control the organic carbon. That's a management issue. So if you can build soil carbon, you buff your soil a little bit more. You get less rapid chain decrease in pH. It goes the other way too, though. A soil that's highly buffered, it takes a lot of lime to make a small pH change. And then, of course, how productive you are on that land. If you are running a lot of livestock, removing a lot of livestock, cutting a lot of wool, baling a lot of hay and selling it, removing a lot of grain, all that production, all of the product that you're removing is effectively an alkali source. And as plants grow, they take up nutrients, they excrete acid into the soil becomes acid, the plant is alkali. We sell the plant material to make money. The more we do that, the faster we acidify the soil. So I put it to you that we're all on the same track. We are all farming, we're removing product, we are acidifying the soil. How fast we're doing that depends on your starting point, your buffering capacity, the type of agriculture you do, but we're all on that same journey. So there'll be some people on alkaline clays that acidity is not an issue for them because they're highly buffered. Their starting point is very high. You've got other people east of, I'm in Wagga, so east of here, in country that the starting point was probably pH 6, and then it's weakly buffered, and they've gotten very good at producing stuff, so they're acidifying that land pretty quick. I know country west of here that's been cleared in the 80s that's quite sandy, and it's only now that they're realising they've got acidity problems on that country because it's so poorly buffered. So yeah, there are no people who aren't acidifying. We're all acidifying. We need to do something about it. We need to balance the system, and that's bringing alkali back into the paddock. That can be done in a few different ways, but bang for buck, lime is a really good way of doing that. Calcium carbonate is lime. The carbonate bit is the alkali. That's the bit that's the superhero that should wear the cape. It's the bit that's changing pH. Calcium is the passenger. It's coming along for the ride. Doesn't do a lot in terms of the plant benefit because there's already a fair bit of calcium in the soil. Just one other thing to throw at you here, because I often hear, oh, but I've got perennials in my system, so therefore I'm not acidifying. The research shows that perennials are just as acidifying as annuals. It came from a hypothesis, a theory that came in the early 90s, that if you had deep-rooted perennials, they would take up nitrate from further down the profile, and that will stop acidification. And it will do that. They will take up nitrate from further down the profile, but that nitrate was created by a process that is acidifying, but in the topsoil. And so whether that deep-rooted perennial takes up the nitrate or not, it's irrelevant. The acidity is formed in the topsoil. So again, we're all on the track. We're all going in the same direction. We're acidifying the soil if we're farming. So how much does that problem hurt us? Largely, we answer that question by doing trials. And so in experiments, we have liming trials where we compare doing nothing to ameliorating the soil or fixing the soil by adding lime, various types of lime, various rates of lime, different ways of applying it. If you're managing a farm or a property, you may do that just by putting test strips out with lime. Maybe it could be different rates, or it could be just, yep, I'm going to put some lime out just in this strip and see what happens, or I'll do half that paddock and I'll see what happens. So that happens. And I just want to say, which is great, like do that, by all means do that and see what happens. But just be careful when you're interpreting what you see. And because I've had conversations with people that, oh yeah, we put a lime strip out and we've never seen a difference, so therefore lime doesn't work. And it's like, well, fundamentally, lime works if the pH increased. Whether your plant responds to give you a performance gain is an associated but different question. If the lime works, the pH increases, and you don't get a plant response, you've got to ask yourself, well, why not? What's happened? And so I say, be careful with the interpretation and go looking. Here's an example. This is Faber beans. This thing had 4 tons of lime in the 2 years before the Faber beans were grown, and so it had lime, and yet the plants were affected by acidity. And so it would be easy to look at that and say, well, I added lime and it didn't do anything, but it did do stuff. These pHs on the left-hand side here are in 2.5 centimetre intervals. So it's 6.5, 5.6. They're pretty good pHs. So that's your top 5 centimetres. And then it goes to pH 4.4, 4.2, 4.1, which is really acid. And so this is saying the lime went on, but it didn't go down deep enough. It wasn't mixed in deep enough to change the pH and remove the acidity, which when you look at the roots on that Faber bean, the roots stop growing when the pH hit 4.4. And so there's an example of the interpretation there isn't lime doesn't work. The interpretation is the lime didn't get as deep as I needed it. Okay, so it basically means that if you're doing strips, and probably I'm going to say whether you see a response or not in the plant or not, always test the soil and see where that pH change happened. Did you remove the acidity? We've got trials, lime trials like you see there on the right, in paddocks where we don't get a response in the plant, and it's like, geez, like you would have expected a response. And then you go looking at the soil data, and the lime hasn't gotten to the worst of the acidity yet. So the plants are all still acid limited. So The issue is incorporation or mixing of lime into the soil, not lime itself. So what do we know? We know lime works to increase pH. That's not rocket science. That's pretty obvious, right? We do know it doesn't dissolve once you get above pHs in calcium chloride of above 7 and 7.5-ish. And that's because the carbonate that's in it needs acid to dissolve. So if there's no acid, it doesn't dissolve. The lime doesn't dissolve. It just sits there. And I've been in paddocks that have had lime put on them, surface applied in the surface 2 years ago, and you can still see the lime. It's sitting there undissolved because the pH in the surface is up around 7 and the extra lime's not dissolving. And I look at that and I think that lime could be in another paddock doing something. We also know that that lime, if the pH is less than 5.5 in calcium chloride, the lime effect doesn't move. So the lime will work where you put it. When the pHs are around 5 and less, 5.5 and less, you'll get a reaction to the lime where you put it, and it will increase the pH, but the liming agent won't move down. It's insoluble, it won't move. Above 5.5, it can move. And so there's this sweet spot. If you can keep your pH above 5.5, but less than 7, any lime that you add will dissolve, and there's a high chance that it will move down deeper into the soil and start fixing some of this at depth. So there's some key little numbers there, and I want you to remember them, because when it comes down to, well, should I be liming and how much lime should I put on? They're important numbers to know, because if you're already up around 7 in the surface, putting more lime on the surface isn't going to do anything. And if you're expecting lime to move deeper, then your pH needs to be greater than 5.5, above the layers in which you want lime to move into. We also know that if you incorporate lime, you get a better mixing, you get a better reaction, it's faster and it's deeper in the soil. But not everyone can incorporate lime, i.e. you've got a perennial pasture, you don't want to rip it up to incorporate lime, or you're on a steep slope and you're worried about erosion risk, which is fair enough as well. Incorporation's not for everyone, but if you can do it, and if you're establishing a new pasture, then yep, like incorporation of the lime that you put on is a great way of getting a head start in that movement of lime down the profile. So just having a look at what I've just been talking about, this is a trial that collaborators at FarmLink have done with us in a project that we call Future Soils. And now Future Soils, it's important to tell you about, it was about picking soils that weren't really badly acid to start with, but were on the margin of becoming acidic to the point that you'd start thinking about liming them. So it was all about preventative action. What happens if you get in front of the acidity? What happens if you try to deal with the acidification before the soils got really acid? And so as a result, when you look at the control here, we've got depth on the y-axis down to 20 centimetres. And I've sampled this, or we've sampled this in 5 centimetre intervals. You can see that the pHs are around 5. So they're not really acid. Like they're not acid to the point where aluminium's, more than 5% or anything like that. Here, aluminium, I think from memory, was like 2 or 3%. So it wasn't too bad. So we picked soils for the Future Soils project. We picked soils that weren't really bad. That said, though, when you put on lime to get to pH 5.2, which was just enough to make the aluminium become not available to plants anymore, what you got was a significant increase. And I can tell you that's significant because these little horizontal bars are called least significant difference bars. And if you can fit them between 2 points, the points are significantly different. So this is the smallest difference that you can have between 2 points for them to be significantly different. So we've got a significant difference here, and only just in this 5 to 10 centimetre layer are these points different. It's right on the margin. And that is what we know from literally decades of work, research and working with farmers, that if you lime to make the aluminium disappear, so you're just liming to around 5.2-ish, but not above 5.5, you never get lime moving. It works where you put it. So this would have been like impacted by even though it was surface applied, it would have incorporated due to sowing. So just the tined implements going through sowing the crops over the years. And this was 3 years. So this was established in 2020, 2023 data. So that's kind of what we saw. What it means is that you don't get movement down. So if you had acidity down here, that lime application doesn't fix it. But then if you lime to a higher pH target, then you get movement to depth. And so this was trying to hit in the 0 to 10, trying to hit an average pH of 5.8. And so I'll tell you right now, I overcooked the books a little bit there. So there's probably a little bit too much lime on there, but that we did get movement further down. So this, without deep incorporation, we've got an increase in pH in our 10 to 15 centimetre mark because lime can move downwards if you keep the pH up over 5.5. And just in case you're interested, what happened if you could incorporate, here's that same rate of lime, but this is incorporated with offset discs, so just what a farmer might have in the shed, so nothing fancy. And you can see there that you got basically a head start. We've got a greater pH to depth in this layer here, and that happened in the first year of application, whereas this surface applied stuff it's taken 3 years to get that line where it is now. It used to be a lot of these points here were to the left. So the lime is slowly moving down because we kept the pH up over 5.5. So that's what's known, right? And so we can use those tools, that knowledge, to then plan our liming strategy. So if we've got acidity deeper down and we can only surface apply it, then we need to be hitting these higher pH targets to allow the lime to move down. If you don't have acidity at depth, then you can still hit that sort of 5.2 mark in the surface because you're not expecting the lime to move down. But what we've seen, especially around our area here, where you're quite productive agriculturally, the rate of acidification is faster than the rate of lime dissolving and lime movement. And so you often get more acidity lower down in this sort of 5 to 15 centimetre mark. And you can kind of see that there's a bit of a trend in that red line, saying that. Now, get out talking to farmers, and one of the guys at Burrumbuttock said, "Yeah, that's great. I can't take your graphs to my bank manager," which I thought that was an awesome statement. I loved it, and it's very true, and I get it. But you've got to, I'm a soil chemist, right? So those graphs are really important to me. But it shows the concepts working, and then you can then look at, well, what does that do to productivity? So what is the gain in production? And so the response depends on the starting point and what you are growing. This is a really, really important. People say, well, what's my production gain going to be? It's like, well, it depends what you've got. If it's a really acid soil, removing the acidity gets you a really big gain. The Future Soil project, the stuff wasn't really badly acid. And so I can tell you that we haven't gotten yield gains in wheat or canola on those sites where the pHs weren't very acid. So where the pHs are all above 4.8, we haven't had big yield responses. You'll see early growth responses, but they don't result in yield responses. Now, if you're cropping, then yield is king. I get that. But if you've got dual purpose wheat and canola, then that early growth matters. And so, but it's difficult for us to capture sometimes too. But we still get early growth changes. We are just highlighting, MLA have funded us at DPI. Richard Hayes leads this project, looking at high performance pastures on acid soils. So the trials that we've been doing over the years, we're using those sites and some new ones to look at, right, once you get rid of the acidity, what is possible? What can we grow? How hard can we push that system? So, and how do those species compete with each other? So that's the new and exciting bit we're doing there. To give you some ideas of production gains on one of our sites. So this is at Morven, and just showing you one of these graphs again. The red line's the control, quite acidic, this one. So it's less than pH 4.5 in that 5 to sort of 20 centimetre mark. So it's quite acid. And we see that sort of shape. It's very common. The pink line is enough lime to get the surface pH, the top 10 centimetres up around 5.2-ish. to make the aluminium disappear. And the green line is if we're putting on enough lime to get rid of the acidity to 20 centimetres. And that's why it's 6 tonnes. Now, we do that experimentally. We're not saying go and put 6 tonnes out. So just always make sure that you're understanding that in our experiments, sometimes we use really high rates just to see what's possible, and to see that that's not going to harm the system. And so we've got that here. We've also got hitting the pH target of 5.8 only in the top 10 centimetres as well, but I don't have the crop production data for that, which I want to show you. You can see the benefit or the reduction in percent aluminium. So this is the percentage of aluminium on the cation exchange sites is decreasing as we increase the pH, and as we increase the pH at depth, we decrease more aluminium at depth. So this green line, it literally doesn't have any plant available aluminium until you get to sort of 15 centimeters, 12 to 15 centimeters, and even then it's 5%. So it's basically removed the acidity. What did that do? So this is canola. So that was established in 2019. Canola in 2020. This is biomass. This was a dual-purpose crop canola, great, and so we got this, a response there. I'm here to tell you, statistically, that is not significant, although this is a tonne more than here. Statistically, it's not significant. The following year in wheat, grain yield, still a dual-purpose wheat, so this thing got grazed. We got more than 2 tonnes extra where we removed the acidity, and noting that 3 tonnes of lime here got the same response as the 6 tonnes here. And that's when you looked at the graphs, these same sorts of graphs from 2021, they were, the green and pink line were very similar. So naturally you get that same sort of response. This canola biomass was in response to grazing. It had already been grazed once, and then we put pasture cages out, and this is the regrowth that happened. So you're getting more, a nice regrowth happening. Trying to put some dollar terms to that, I want to just share some data here. This is Matt Dunn's work from a GRDC funded cropping sequence trial. John Kierkegaard oversees this over 4 sites. Matt Dunn controls 2 of them. And I'm going to show you here system gross margin, dollars per hectare per year over a 5-year period. And so the sites were at Condobolin, Urannah, Wagga and Grenthorpe, and they had a barley, canola, wheat rotation. And there's your gross margin per year at those sites. Okay, so there are differences in those sites for rainfall and soil type and that sort of stuff. When you include a legume in that system, the gross margin with these, so this is a faba bean or lupin canola wheat rotation. Now, I want to point out here that the difference in this, you effectively have some positives and negatives here. And where the negatives are, you got a negative or a loss, a difference. You suffered a reduction in profit or gross margin gain when you added a legume to the system when the soil was acid. Okay, so Grenthorpe used to be acid. They put lime on and incorporated it to 20 centimeters and removed the acidity. And now the legumes are more, that legume in the system is more profitable. And that work, the benefit of the legume wasn't only in the year of the legume, it's the benefit to the system of the legume. That's nitrogen that you don't have to buy. Okay, so I want you to look at those numbers and see there's a system benefit to removing acidity. It's not just about production gain, it's also about the savings that come from having functional legumes in the system. That's important. In pasture context, so this is, I'm going to create a table here that is all stuff that's been published in the literature. It all had a control, like lime control, unlimed control, and then they limed plots as well. And so we can compare the response to lime is the gain over the unlimed control, and then that response as a gross margin compared to no lime. So what we have, the first one is a trial that was done east of Wagga called MASTER, Managing Acid Soils Through Efficient Rotations. And it was a long-term trial, and it had sheep-based, had annual and perennial pastures. What I'm showing you here is the perennial pastures. And the response to lime over the period of time was an extra 3.8 DSE, which represented a 25% increase in carrying capacity. There was also a 25% increase in pasture production. And when you had legumes in the system, work that Richard Hayes did, I'm going to say in 2007, showed that the gain in nitrogen fixed from the atmosphere was virtually the same proportion of the gain in dry matter yield. So that 20% production gain was probably, where there were legumes in the system, you're probably getting about 25% extra nitrogen as well from the atmosphere. And so this was published in 2006. So this gross margin is based on commodity prices leading up to 2006, which were pretty poor, to be fair. So that's $25 per hectare gain due to liming based on those commodity prices. This is up north at Ebor, cattle, 16% more production in beef, and it was a $89 gain in gross margin, 2003. This study was so 5 years around the end, 1999, 2004, sheep-based. Liming got you an extra 2.5 DSE. Liming plus annual super got you 5.6 DSE. And the numbers here are really interesting. So this work showed that liming, you actually lost money, but you still gain money as long as you put the super out with the lime. And when you go into the data and look at the numbers here, it was really only, I think it was 2003, was drought. They fed sheep instead of offloading them, and all of the money for the feed went on the bill, and that's what drove the gross margin down. But in the years that I've seen of that data, there was only 1 year where they lost money. All the others were positive. But this shows the benefit. When you remove the acidity, you then have a new plane of nutrition that you've got to meet to get the productivity happening. And you get the gain by adding the livestock. Okay. And more recently, so this is 2015 to 2020, 2.9 DSE gain. So you can kind of see same sort of numbers keep appearing here in the gain. But here the gross margin was $181 extra because the commodity prices were so much better. And so what I put to you here is that these were acid soils, so they should have been responsive. And when you limed and removed the acidity, the response was like this, and it's roughly around about a 25% increase in productivity on those acid soils that were responsive to lime because they were so acid. And that's the gain in productivity. How much that converts into a gross margin is highly dependent on commodity prices. And work that that John Francis did used that same master data that I just showed you, that the first one in that table, and compared 2007 commodity prices versus 2021 commodity prices. And so here's our profit from the investment of lime. And you can see that when commodity prices were low, it's a flattish line, and the point where it crosses zero and starts getting into a profit is around about there-ish, sort of 10 years. Whereas when the commodity prices are high, you get a much earlier payback period and into a gain. And so highly sensitive to commodity prices. The cost of lime hasn't really increased that much. It has a bit, hasn't increased that much, but really sensitive to commodity price. Now, we don't know what commodity prices are going to do in the future, so cash flow is important. I get that. So do I lime or do I not lime? Comes down to cash flow, but it would be, there's a conversation that you have to have with yourself about, if I don't lime because commodity prices are poor, my cash flow is poor, I'm still going to have to lime down the track. But what that does, it postpones the gain in productivity that I'm going to get. So when commodity prices do get better, you'll have this little lag phase in productivity that you'll be catching up to. And so I'm not judging anyone. I understand the situation there. It'll come down to cash flow, debt load, and everyone's different. So, but that's a point that you will have to grapple with. So how much lime and when? You've basically got to know your current situation. And from where I sit, that's done by soil testing, by you getting out and having a look at your pasture composition, digging some holes and having a look at what the roots are up to. Do you have legumes? Are those legumes nodulating? Are they doing what you think they're doing? So some observational stuff. Looking at pasture composition, looking at roots costs you nothing. So it's a time thing. It's not a money thing. With the soil testing, everything I do, I just keep coming back to, if you want to know, sample in 5 centimetre increments to 20 centimetres, measure Colwell P, pH, and exchangeable cations, including aluminium. That suite of tests costs less than $40 per layer. So it's $160 per 20 centimetre sample, if you like, if you look at it that way. And what that does, why the 5 centimetres is so important. Here's our soil depth down to 20 centimetres. Here's our pH on our x-axis. If you just do 0 to 10 soil sample, the number can come back here. This is it. It's 5.2 because a 0 to 10 core averages whatever the pH is in that 0 to 10. It just averages, and you'll send off to lab. You get the number back, and I'll say it's 5.2. And you'll look at 5.2 and think, I don't have an acidity problem. Had you measured that same soil in 5 centimetre increments, you can see it'll often look like this, where the pH is higher in the surface 5 centimetres and then much lower in the next 5 centimetres. And so if you knew that you had a layer in this 5 to 10 centimetre layer that was a pH 4.5, you would know you'd have an acidity problem. So that's worthwhile knowing. The plant will know. So if you just did 0 to 10, you'll think you don't have a problem. Your plant will still know it's got a problem. Going down to 20 centimetres allows you to see the trend in the pH. So this is good because it allows us to, we've got different interpretations to make here. The red soil, which is acid to depth, is a long-term problem. We can work at that, we can chip away at that, maintaining a pH up over 5.5 in the surface and allow lime to move down. If you wanted to do intensive like cultivation, like to 20 centimetres, you could do that, but there's extra cost to that. The blue line really doesn't have much of a problem, and it's close to the surface. So we could fix that with cultivation, incorporation of this higher pH surface. Both of these soils had a liming history, which is why the pH is a little higher at the surface. Or it could be, I know this is up around 6. I know it's had lime recently. That lime will move. Or if it hasn't had lime recently, any lime I put on this, maybe 2 tons, I'll get lime moving down deeper in and to get rid of this acidity here. You got to ask yourself, what's the existing pasture quality like? Are there legumes present? Is it likely to be responsive? The species that I've got there, are they going to respond? So you've looked at the situation you're in. Am I establishing a new crop? If you're establishing a new crop, then and you can cultivate that blue line, you could add lime and incorporate that in. You would remove the acidity problem, and you'd be able to establish acid-sensitive plants, and you'll go well. Doing that to that same thing to the red line, you'll still have an acid-limited pasture, and so that might just change what your expectations will be. You can. If that was a permanent pasture already, an existing pasture, then I know putting lime on the surface will fix this acidity at 5-10 centimetres within a couple of years, but you're still going to have acidity in this red soil. But if the strategy is, if that's what you want to remove, then maintaining the pH above the acidity that you've got, keeping the pH above 5.5 and adding lime to it, you will eventually keep chipping away and remove that acidity. So doing nothing is not an option on acid soil. So if commodity prices are bad and drought forecasting is possible. Doing nothing is really not an option. You still need to understand your situation. You still need to get out and have a look at your current situation. Do that soil testing so you can monitor the changes that are happening through time. Have a look at how the pastures are responding to the conditions that you've identified in that soil test. Consider your production needs. In that table I showed you with the gain in DSE and then the gross margins that were possible from that, they all relied on capitalizing on removing the acidity by increasing productivity by carrying more livestock. So if you don't want to carry more livestock, then you're not likely to get a big response in productivity. Your pastures will be better. You'll get more organic matter. The environmental condition of your property will be better, but your gross margins won't be in the short term. So you've got to be able to capitalize on that production. There's no substitute for alkali to fix acid soils. So I want you to resist the temptation of trying to band-aid fix acidity by putting phosphorus on your acid soils, thinking that it's removing the problem, because it's not. Adding molybdenum, same deal. They're just band-aid solutions to an underlying problem, which is your acidity. And I know I've speak to growers, speak to consultants, and I know people that go, oh, but you'd go with P and you'd go with Molly so you can make enough money to afford the lime. And the problem is that the people that say that and the people that do it are humans. And you know what humans do? They do things that aren't what they originally planned. And so they might do that. They might get the money. They might spend that money on something else, and that paddock misses out on the lime that it needs. And as you go through time, you're more productive, the soil acidifies more, your P becomes less efficient. You need to put more on to get the same sort of responses that you used to get. And then when you do go liming, all that moly that you've been putting on over the years potentially can become toxic, and that can be a problem. We've seen that a couple of times. There is no one right time or situation, right? So there's no, this is what you should do, but you need to have a plan. You need to have a liming strategy. You need to know what your soils are in terms of their pH profiles from those 5 centimetre testing to 20 centimetres, know what they are, and work out, what am I trying to do here? Am I going to live with that acidity, or that little acid layer that's formed that, look, it's only formed over the last 10 years. If you've got some soil data, then you go, right, well, let's nip that in the bud now. Let's get some lime on that and remove that acidity so that we can keep those legumes being productive for us. Prioritise your paddocks based on expectations. So this comes down to what you expect of that country. And I'll give you some examples of that now. And that's going to fit into a long-term plan. Liming's a long-term thing. So it doesn't, you might know you've got a problem now. It doesn't mean you have to solve it now or fix it now, but you can chip away at it, and you can decide, okay, now commodity prices are good, or now I've got that debt cleaned up a little bit. I've got this money. I can now get that lime on. I know I needed it. Now's my opportunity. Let's do that now. Or I know I need to sow that pasture, sow a new pasture in that paddock, clean it up. Now's my time to get that lime in, because that's my chance to incorporate, my window of incorporation. So let's look at, on your farm, you might have a high performing paddock and you might have a paddock that's poor. And the poor paddock, you got to ask yourself, well, why is it poor? Is it just that? Is it the soil type that's there? Is it the topography? Is the aspect? Is it its history? So there'll be reasons for that. And some of that you might be able to look at soil stuff. Some of it you might know because you've farmed that country for decades. It might be new land to you. You need to work it out. So digging holes is an option. Looking at plants is useful there. Is it likely to respond? So that's, what are you growing? Are the things that you're trying to grow there going to grow better at a higher pH, higher plane of nutrition? Are there legumes present? So I keep talking about legumes a lot because, one, they're responsive to improving pH or removing acidity, and two, they fix nitrogen. And once you've got that, that changes your productivity of your system. Are you going to sow a new pasture or not? Okay, so if you've got like I've said it before, I'll say it again. If you're going to sow a new pasture, that is your opportunity to really to lime. If you've got an acid soil, there's your window. If you're not doing it, then you're never going to do it. In a high performance soil, when was your last soil test? I know from my own experience on our place, we had really high performing paddocks, and when they weren't monitored correctly, their performance dropped off because their acidity increased so much to the point that all the legumes failed quickly and then there was like, geez, what's happened here? And that's when it was diagnosed as an acidity problem. I've been on properties where people say, can you come and have a look at this soil and do some soil testing here? You know, it used to be a good paddock and now it really struggles. You take the soil sample and you're writing on the bag, what's this paddock called? Oh, it's the hay paddock. You know, so they've cut hay in that thing for years and years and years, removed all this alkaline, just turned it acid. And so having those soil tests and a history of them can tell you whether these high performing paddocks are actually declining in their fertility or not. And allows you to then address it and do something about it before failure. Because if you do nothing, when they fail, it's all of a sudden, there's this tipping point where all of a sudden, you know, your legumes drop out and then the system fails. Or you become reliant on spreading urea on your pastures to make them function. What is the trend through time? So having a history of it is important. So unfortunately, there is no simple answer. The decision is based on the individual. It comes down to what you're trying to achieve. Are you trying to increase productivity? Are you trying to increase fertility of your soil, leave it in a better place? Financially, there's a whole bunch of financials, that cash flow, how much debt. There's all these things that make it impossible for one person to say, this is what you should do. Okay. Just want to leave you with this. Not all production is equal. And so we can do trials that look at yield and dry matter and that sort of stuff. But when it happens is important. So this is Manus, and this is a site that's run by Holbrook Landcare. So Nick McGrath at Holbrook Landcare is the soils guy there. Fantastic guy. Knows his soils well. So this is Manus, which is up near Tumbarumba. And on the left there, you can see one of our lime trials there. Roughly where the tray of the ute, the tailgate of that ute is, the photo on the right is where that photo is taken from. And you can see on the left, that is the lime plot, and on the right is the control unlimed. So this was just only a week ago. And so you can see the green stuff. Now the green stuff is worth a lot at this point in time. And so the work that was done by Matt Lischke at Lagan, that work, the gain in productivity that they got from lime there, he did the work that showed it actually came from early response in pasture growth to early autumn rains. So the pH was high due to the lime in the surface. It rained, the clovers responded, they fixed nitrogen, and then the grasses took off. That was the difference. It wasn't the difference lasted through time, but the response happened when you really actually needed the feed. And so we've got people at Lime a lot, we talk with them. You hear about what liming has done is extended the shoulder of the feed curve. So you've got earlier growth and you've got better later growth in their lime country is what we hear. And that's what you see in that photograph. And there's one more. This is the university farm here at CSU. And you can see this satellite image, those green stripes going up and down the page. They are a historic liming trial that was done 1989. And this is Lucerne in the Millennium Drought. And you can basically see those dark patches are where the paddock had been limed. And so the lime keeps giving back, but it gives it back. Lime repays you when you need it most, which is when conditions aren't wonderful. So you've got a more resilient system to the climatic conditions that you're facing. You've got more ground cover, so there's a lot of benefits from that to your system. And yeah, so just thanks for that. Thanks for listening. And again, thanks for all the people that work with us, especially the growers that allow us onto their property to do trials, and the consultants that talk to us and say, hey, heard you speak. What about this? Or have you thought about this? Or we've seen this. what are your thoughts? So we just learn all the people that you see in that list and a bunch of people who aren't named. We're just learning all the time from them. People's experiences are what we bounce off. So thanks very much.
Thank you so much, Jason. I know I've been madly writing notes as we go through tonight. So just while I get the screen up to share, we have a few questions to get through. So I'll get straight into them. The first one that's come through tonight, Jason, is how can you decide where to start if you have soil tests for all of your paddocks?
Yep. So again, it comes down to what you're trying to achieve. If you're trying to see short-term responses, then you put the lime out in the paddocks that are more likely to respond based on having lower pHs, but having plants there that are going to like having a better, higher pH. And if it's an existing pasture, have I got legumes there? Then that would be where I'd be putting my lime out, because you know they're going to respond to that, if that makes sense.
Yeah, great. Thank you. And if you don't put enough lime on, is it still worth it?
Well, that's how long is that piece of string? So enough lime. So it depends. How much lime depends on what your starting point is and what you're trying to achieve, right? So if you've got a paddock that is affected by acidity, so the pH is 4.5, 4.6, so it's low, then we know if you get that up over 5, so either by putting on lime and incorporating, so you're not expecting it to move, you're not asking it to move, you've incorporated it in, then getting the pH up around 5 will get you rid of that acidity in the depth that you've mixed that lime to, and then you'll be away. So if that took 2 tonne, then 2 tonne is what you should do. If you put 1 tonne on and you don't remove the acidity, then you'll still have an acid affected plant and it's not going to perform very well. So in that case, not putting enough on to get to your target hasn't helped. You would have, and even in some of our trials, we've got a treatment where we call it little and often. And so we're not calculating lime an amount rate to fix 10 centimetres of soil. We're asking it to only do the top 5 centimetres, and we're going to monitor that and just keep topping it up. So it's always above 5.5. And when we did that, what you saw is you never saw a big response to the plant from the plant, because it still had acidity in the soil. So even though you've given it some of the medicine, it was never over the illness. Whereas when you put enough lime on to remove the acidity in one hit, the acidity was removed, the plants took off, and they just, it was a phalaris and clover pasture. The phalaris just went whack and grew like stink. And, and so I saw that, and the message I took from that was, if it's acid, fix the problem. If you're trying to maintain something, then little bits help for that maintenance. But if it's sick, it's kind of like, I've cut my arm, I'll put a Band-Aid on that. I really need 7 stitches, but I'll put that Band-Aid on. Oh, geez, now the Band-Aid's full. I need to put another Band-Aid on, put another one on, put another one on. Would have been better, I just went and got that stitched, and then I'd be right. So it's like, fix the problem, move on. So another way of talking about that, Cassie Chafe talks about, don't fairy dust your farm. Don't put a splattering out that costs money but never actually achieves anything that returns money. You're better off putting it somewhere, fixing a problem, getting the response off that, and then lining up your next paddock that's going to be the one that you're going to target.
Great. Thank you, Jason. That's a really good take home for everyone. That on the other end of the spectrum, can you add too much lime, particularly calcium, to soil?
Yeah, so we've not seen it with calcium, and so the concern there for us anyway, and people for sure, let me know if you think I'm missing the point, but for me the concern was you can get mineral imbalance. If you've got too much calcium, you'll often get magnesium deficiencies, for example. And we haven't seen that in the places where we've gone looking at tissue testing. We haven't seen that. We were concerned about it, especially in young dual-purpose wheat, so grazing wheat. And when you look at the tissue test, there's a bit of a trend there, but not enough to trigger like a threshold. And then the other part of that is the people that were grazing that wheat. The best practice is to have mineral supplement in there with it as well. And so when you do that, you kind of remove any livestock health issues. And we haven't seen any problems due to high calcium in the tissues that we've sampled. What we have seen is in 2022, we got pastures and crops affected by molybdenum toxicity in our high lime rate plots. And to give you an example, one of the trials that we had at ACT, the best plot in 2021 was the incorporated lime at our highest rate at that site. That was the best plot. And the farmer's response in seeing that was to go and buy a piece of machinery to do all the incorporation of his farm, because that was it. He said, I just want more of that. And then 2022, that same plot was the worst plot. And we tissue tested because it looked really sick, and it was molybdenum toxicity. And we said to him, do you put out molly fertilizer? And he said, I've run this place for 10 years. I've never put molly out. And so we think it was just historic molly that's being put on back in the day when you had molly super put out. And in acid soils, that molly would have gone into the soil, and what wasn't taken up by the plant would have gone into the soil, converted into an unavailable form and sat there. And next year, molly went out and did exactly the same thing again. And then we've come along and limed it. And in that 2022, which was wet and cold, and I don't know why, you go to the international literature and there's nothing there about it either. So it's a new thing for us. But then cold and wet, molly sitting in the ground, and we've increased the pH, then it released for whatever reason. 2021 wasn't a problem. 2023 wasn't a problem. And so we've seen that we saw that same sort of effect in 3 sites, and it was only ever in 2022 we did glasshouse trials and stuff, and so we know it was molybdenum toxicity, but we only ever seen it in 2022. And so what that says, the important part of that is, if you've had a history of putting molly out and now you lime, don't put molly out anymore. You won't need to. So I know people that, if they grow canola, you put molly out. If you're putting in a new pasture, you put molly out. If you've limed, you won't need to, but it would be good, smart pool if you tissue sampled, your agronomist tissue sampled through the years, just to see that you didn't run into a molybdenum deficiencies, because we don't know how long, or we don't understand enough about that chemistry, and we don't know why it was that wet year. So there's a bit more work to do there in that space. It's quite interesting.
That's very interesting, Jason. You're fixing one problem and creating another in a way.
That's how life works. Yep.
Exactly right. We're right on the end of time, but there's one more question that I'd like to ask you, and then anyone's question that we don't get to, I'll make sure that we address it in our podcast. So for those listeners that have an unanswered question, tune into the podcast to get the answer to that one. So we have a very acid soil of 4.1, direct disc seed only. What time frame would you think they're looking at for our lime to reach 10 centimetres?
And only self-supplied?
Yeah.
Yeah. So interestingly, we've got that Menace trial. We've got pH change down to 20 centimetres after 3 years there. Now, it also gets about 950 mils of rain each year. So, depends where you are a bit. The more rain you have, as long as you keep that pH up over 5.5, the lime will move down. The work that we have done, given the rainfall that we've had in 2021, 2022, from our work, I would say 3 years you would have a pH change at 10 centimetres, as long as you hit that pH target. And if it doesn't rain, then it's not going to be down at 10 centimetres. Like, do you know what I mean? Like but I'm surprised. Like I always thought it would take 15 years for that lime to move down, and we got changed that Temora data I showed you. We had pH change. There wasn't a lot of difference between surface applied lime and stuff that had been incorporated with offset discs after 3 years. Manus has got lime down to good depth in 3 years. The key is having that pH above 5.5.
So the key is pH above 5.5 in the top so that the lime can then move.
Yep. So in the layer above where you want it to get to. Yep.
Excellent. Yep. Thank you so much, Jason, and thank you to everyone who's joined us for tonight's webinar. I'm really looking forward to continuing this conversation in the podcast because there's a few more questions that we can get through. And thank you, Jason, for sharing some really great information on how producers can make some of those liming decisions with that focus on maximising returns. For those that attended tonight, if you have any additional questions or suggestions for future topics, please reach out by completing the survey at the QR code on the screen. This is really important. It helps us to guide the direction of future webinars and also to make sure that we're meeting your needs. If you're listening to the recording of this webinar, please also complete the survey. Thank you all again for attending, and we look forward to you joining us for our next webinar, which will be on the 8th of May. We'll be changing tact a little bit. We'll be hearing from Anne Collins about maximising Dorper reproductive performance in challenging environments. If you missed last month's webinar, head over to the MLA or Agrista website to watch it. And as I've given a few tempters into listening to further questions, be sure to check out our podcast series. You can find this on all major podcast platforms under the Productivity and Profitability Media series. So happy listening, and thank you again, Jason.
Thanks.